Dear students, this video explores various techniques for log data analysis. Here, we outline various techniques used for analyzing log data, ranging from manual methods to machine and deep learning approaches. The most basic method involves a human reading through log lines. While this can be effective for small logs, it becomes impractical for logs with thousands or millions of lines due to the overwhelming volume of log lines. The next step up is query-based techniques, such as using grep to search for specific terms like UI daemon screencaster stop. This approach allows users to quickly narrow down relevant parts of the log using domain-specific knowledge. Another practical method is diff-based analysis, where two logs, typically a good log and a suspect log, are compared to identify differences. Tools like diff, kdiff3, or beyond compare can help automate this comparison. Building on this, rule-based approach can automate the process once suitable keywords have been identified. For example, a rule might be set to check if UI daemon screencaster stop appears in the logs and trigger a specific action when detected. These four methods, manual reading, query-based, diff-based, and rule-based, can be used together to complement each other. Moving into statistical methods, statistical learning, machine learning, and deep learning. The core idea is to measure the distance between logs. For instance, we can measure the distance between two logs, such as a good log and a suspect log, using metrics like Jacquard similarity, cosine distance, or compression distance. When comparing a suspect log to a group of good logs, multiple distance measurements between pairs of logs can be employed. However, this approach can become computationally expensive as the number of log pairs grows exponentially with the size of the dataset. Additionally, interpreting multiple distance measurements can be challenging as it requires understanding the differences across numerous comparisons. To address this, we can build a model that captures the characteristics of good logs. In such cases, unsupervised anomaly detection models are particularly useful. These models assess the distance of a suspect log from a set of good logs by using algorithms such as k-means, isolation forest, or autoencoders to identify deviations. Lastly, supervised learning methods can be used to define a decision boundary between normal and anomalous logs. These methods require labeled data to train models and include algorithms such as logistic regression, decision tree, or random forest. However, obtaining sufficient labeled data in industrial contexts is often challenging, which limits the practical applicability of these techniques. Now we look into how to measure the distance between two log files using Jacquard distance, a method commonly used for comparing sets. We begin with two log files, good.log and suspect.log, representing normal and anomalous behavior, respectively. To apply Jacquard distance, logs are transformed into sets. This could be sets of words extracted from the logs or parsed sets of log events, such as E1, E3, E4. Jacquard similarity measures the overlap between the sets, calculated as the size of the intersection divided by the size of the union. For example, 1. Good.log contains E1, E2, E3, E4, and suspect.log contains E2, E3, E5. 2. The intersection is E2, E3, two shared events. 3. The union is E1, E2, E3, E4, E5, 5 unique events. Therefore, Jacquard similarity is 2 divided by 5 or 0.4. Jacquard distance is then computed as 1 minus Jacquard similarity, which gives 0.6 in this case. This metric quantifies how dissimilar the two log files are, providing insight into how much the suspect log deviates from expected behavior. This method still adheres to the two-file approach but incorporates statistical analysis for a more repeatable log analysis process. Here, we outline an approach for anomaly detection by comparing one log file to multiple reference logs using k-means clustering. Consider a set of logs representing normal behavior, such as good1 log and good2 log, alongside a single log suspected of containing anomalies, suspect log. This method uses clustering to determine whether the suspect log deviates from the normal operations. First, all logs are transformed into structured representations, such as word lists or event sequences for analysis. The normal logs are then used to build a model. K-means clustering groups these logs into clusters, with each cluster represented by a centroid reflecting typical behavior. The suspect log is introduced into the model and its distance to the centroids is calculated. This distance indicates how similar or different the log is from the clusters of normal logs. If the distance exceeds a defined threshold, the suspect log is flagged as an anomaly. This method uses multiple historical log files to systematically detect deviations, providing a clear way to identify potential issues. A link is provided for further explanation of k-means clustering. This slide explores a similar approach, but this time using a deep learning method called autoencoders. The process starts with multiple reference logs, good1 log, good2 log, that represent normal behavior, and a single suspect log to evaluate. Again, the logs are first transformed into structured representations, such as words or event sequences. Using this data, an autoencoder model is built with the good logs. The autoencoder compresses the logs into a reduced latent space using an encoder and then reconstructs them back to their original form with a decoder. This process captures the key patterns of normal logs. When the suspect log is introduced, the autoencoder attempts to reconstruct it. The difference between the original suspect log and its reconstruction, called the reconstruction error, is measured. If this error exceeds a defined threshold, the suspect log is flagged as an anomaly. A link is provided for further explanation of autoencoders.